Engineers said it was impossible, but SpaceX just revealed metal heat shields that survive 2,000 degrees Celsius using rocket fuel as coolant. Yes, the same methane-powering Starship is now protecting it from melting. But here's what shocked everyone. Ceramic tiles kept failing, costing millions in repairs. So why risk a $500 million rocket on untested metal? What happens if the cooling system fails during re-entry? And how does this change everything we know about space travel? Flight 10 will answer all these questions in the most dangerous test yet. Let's dive right in. Here's the terrifying truth SpaceX engineers discovered after Flight 9. Every single ceramic tile costs $1,000 to manufacture. With 18,000 tiles per Starship, that's $18 million just sitting on the outside of your rocket. But here's what shocked everyone. Tiles weren't just expensive. They were falling off like dominoes. Flight after flight, SpaceX watched helplessly as their carefully crafted heat shields cracked, chipped, and detached. The payload bay doors that will deploy those 10 simulated Starlink satellites on Flight 10, they malfunctioned partly because ceramic tiles couldn't handle the thermal stress. Engineers spent months redesigning the mechanism, but the root cause remained unchanged. Think about this for a second. The Space Shuttle Columbia killed 7 astronauts because of one missing foam piece. Now imagine 18,000 potential failure points, each one capable of turning your $500 million rocket into space debris. Every tile that falls off creates a domino effect. Neighboring tiles experience increased stress and start peeling away during the most critical moments of re-entry. But what if I told you SpaceX found something that shouldn't exist according to basic physics? Flight 6 revealed something that defied every engineering textbook. Under extreme heat, Starship's stainless steel hull developed microscopic crystals that actually increased its thermal resistance. This wasn't planned. It was a complete accident that could revolutionize materials science forever. Picture this. You're expecting your metal to weaken under 2,000-degree heat, but instead it gets stronger, like a muscle that grows under stress rather than breaking down. SpaceX's metallurgists couldn't believe their instruments. The same steel that should have been melting was developing internal structures that fought back against the inferno. This discovery sparked something revolutionary. If steel could naturally evolve heat resistance, what if they engineered it from the beginning? Enter the impossible metal heat shield, technology that every aerospace engineer said would never work. Metal conducts heat. Metal melts. That's basic physics, right? Wrong. SpaceX just proved that basic physics has some very big blind spots. Here's where SpaceX pulled off engineering magic that sounds like science fiction. They're using rocket fuel as coolant. Yes, the same methane that powers Starship is now protecting it from becoming a fireball. This sounds completely insane until you understand the genius behind it. Water boils at 100 degrees Celsius. Liquid methane stays stable at minus 162 degrees Celsius. It can absorb massive amounts of heat before turning to gas. But here's the brilliant part. As methane absorbs heat and becomes gas, it gets fed directly into the Raptor engines. Zero waste. The same molecule that protects your ship from burning up also powers its flight. It's like having a car that runs on its own coolant. But this creates a nightmare scenario that keeps SpaceX engineers awake at night. What happens if even one cooling channel fails during re-entry? You go from protected to dead in milliseconds. There's no gradual failure like ceramic tiles. Metal failures happen instantly. One moment you have a working heat shield, the next moment you have molten metal flying off your spacecraft at 17,000 miles per hour. Ship 37 carries SpaceX's most dangerous experiment yet. Hidden beneath those innocent-looking metal tiles are pressurized methane cooling systems with microscopic channels thinner than human hair. These aren't passive heat shields. They're actively fighting the inferno of re-entry using real-time temperature monitoring and automated cooling flow adjustments. Think of it like blood vessels in your skin. When you're hot, vessels expand to release heat. These metal tiles work the same way, but with supercooled rocket fuel instead of blood. The system monitors temperature thousands of times per second and adjusts cooling flow automatically. But here's the terrifying part. If even one channel clogs with ice crystals or gets damaged by debris, the entire section could fail catastrophically. Unlike ceramic tiles that crack gradually, giving you warning signs, metal systems fail without notice. 1 microsecond you're protected, the next you're watching molten steel peel off your rocket. So why would Elon risk a $500 million vehicle on technology that could kill everyone aboard if it fails? The answer will shock you. Every ceramic tile replacement costs SpaceX $1,000 plus installation time. After each flight, teams spend weeks crawling over Starship like surgeons, checking every tile for cracks, loose edges, and heat damage. Some flights lose dozens of tiles during ascent alone. This isn't sustainable for a rocket that needs to fly like an airplane. Metal tiles change the entire game. They're stronger, cheaper to produce, and designed to handle dozens of flights without replacement. Instead of $18 million in ceramic tiles that need constant babysitting, you get a robust metal system that could last 50 flights with minimal maintenance. But there's a bigger prize at stake. NASA's Artemis moon program requires rapid reusability. Military contracts demand quick satellite deployment. The future Mars missions need rockets that can refuel and launch within hours, not weeks. The first company to crack this code wins the entire space economy, worth hundreds of billions of dollars. Current ceramic systems make airplane-like operations impossible. You can't have same-day turnarounds when every flight requires extensive tile inspections and replacements. But metal heat shields with integrated cooling could make space travel as routine as commercial aviation. There's just one problem. This technology has never been proven in the brutal environment of orbital reentry. Ship 37 sits in Megabay 2 right now, receiving final preparations for what could be the most important flight in spaceflight history. Teams are installing experimental metal tiles alongside traditional ceramic ones, a hybrid approach that hedges their bets while testing revolutionary technology. But Flight 10 isn't just about heat shields. Ship 37 must deploy 10 simulated Starlink satellites weighing 1,900 kilograms each, reignite Raptor engines in the vacuum of space, and survive a controlled splashdown in the Indian Ocean west of Australia. Each objective pushes the boundaries of what's possible. The stakes couldn't be higher. If the methane cooling system fails, SpaceX loses not just Ship 37, but potentially years of development time and hundreds of millions in investor confidence. Stock prices would crater. Competitors would smell blood in the water. NASA might reconsider their partnership. But if it succeeds, SpaceX revolutionizes space travel forever. Every future spacecraft will copy this design. Ceramic tiles become obsolete overnight. Rapid reusability becomes reality. Booster 16 adds another layer of insanity to this already impossible mission. For potentially the second time ever, SpaceX will attempt to catch a 230-foot, 200-ton booster with Mechazilla's robotic chopsticks. Miss by inches, and you destroy both the booster and the launch tower in a spectacular explosion visible from space. Why would they attempt two revolutionary technologies on the same flight? Because SpaceX is running out of time. NASA expects Artemis moon landings by 2026. The military wants rapid satellite deployment capabilities yesterday. Commercial customers are already shopping for alternatives. Elon's strategy is pure Silicon Valley disruption, move fast and break things. Instead of testing one technology at a time over years, they're validating multiple systems simultaneously. It's incredibly risky, but it could accelerate development by decades. The booster catch alone proves that Starship can land precisely enough for Mars missions. The metal heat shield proves it can survive re-entry repeatedly. Together, they validate the entire concept of rapid reusability that makes Mars colonization economically feasible. Here's what makes Flight 10 even more revolutionary. Ship 37 might be the first to fly with Raptor 3 engines. These aren't just upgraded Raptors. They're completely reimagined propulsion systems that look like skeletons compared to the flying spaghetti monster of Raptor 1. Raptor 3 produces 280 tons of thrust, 30% more than the original design. It weighs 400 kilograms less while delivering 50 more tons of power. The engine looks so stripped down that United Launch Alliance's CEO initially thought SpaceX was showing fake photos. But here's the secret sauce. Raptor 3 engines generate so much less external heat that they don't need protective shielding in the engine bay. This eliminates another failure point and reduces vehicle weight by thousands of kilograms. More thrust, less weight, fewer parts to break. Combined with metal heat shields, Raptor 3 creates a self-reinforcing system where every component protects every other component. The engines run cooler, reducing heat load on the shields. The shields protect better, allowing engines to run at higher performance. It's engineering synergy at its finest. Flight 10 represents the culmination of 14 years of Raptor development and 23 years of SpaceX's existence. Every lesson learned from Falcon 1 explosions, every Dragon mission, every Falcon 9 landing led to this moment. The metal heat shield technology being tested could either validate SpaceX's entire approach to reusability or send them back to the drawing board. But here's what competitors don't understand. Even if Flight 10 fails catastrophically, SpaceX wins. They'll learn exactly how metal cooling systems fail under real conditions. They'll iterate, improve, and fly again within months. While competitors spend years studying the problem, SpaceX will have solved it through actual testing. This is SpaceX's superpower, the willingness to fail fast and learn faster. Traditional aerospace companies would spend a decade modeling metal heat shields in computer simulations. SpaceX builds them, flies them, watches them fail, and builds better ones. The metal heat shield on Ship 37 might save SpaceX billions in future development costs, or it might provide the most expensive engineering lesson in history. Either way, humanity gets closer to becoming a multi-planetary species. But there's one final twist that could change everything we think we know about the future of spaceflight. Here's the twist that changes everything. SpaceX isn't just testing metal heat shields for Starship. They're secretly developing this technology for something much bigger. Elon recently hinted that Block 3 Starship will be 12 meters wide with 42 Raptor engines, producing 3 times the thrust of the Saturn V. But that's not the real twist. The metal cooling technology being tested on Flight 10 is designed to work on Mars, where ceramic tiles would be impossible to manufacture or replace. This isn't just about reusability on Earth. It's about building rockets that can be maintained on another planet. Think about it. When the first humans land on Mars, they'll need to refuel and launch back to Earth. Ceramic tiles require precision manufacturing facilities that won't exist on Mars for decades. But metal heat shields? They can be 3D printed from Martian iron and repaired with basic tools. Flight 10's metal cooling system could be humanity's first step toward truly interplanetary spacecraft. We're not just watching a rocket test, we're witnessing the birth of technology that will carry our species to the stars. What do you think happens when SpaceX proves this works? Will Boeing and Blue Origin scramble to copy this design, or are they already too far behind? Let me know your thoughts below, and if you want to stay ahead of the space revolution, hit that subscribe button. The future is about to get very interesting. $268.9 bar, one number that just shattered Russia's 30-year dominance. America was so dependent on Russian rocket engines that we paid them $10 million per engine for our own military launches. Then SpaceX did the impossible. But how did Elon Musk's team crack the code that stumped NASA for decades? What secret fuel gives Raptor its insane power? And why are the Russians suddenly scrambling to catch up? Let's dive right in. Picture this nightmare scenario. It's the height of global tensions, and America's most classified military satellites can't reach orbit. Why? Because we ran out of Russian rocket engines. This wasn't science fiction. This was America's reality for over 20 years. It started innocently enough in 1995. The U.S. Air Force had a brilliant plan: spend $1 billion on the next generation of American rockets. Boeing got the contract for Delta IV. Lockheed Martin built the Atlas V. Both companies had one tiny problem. They had no engine powerful enough to make their rockets work. Meanwhile, across the globe, Russia was sitting on a technological goldmine they'd inherited from the Soviet space program, the RD-180 engine. This wasn't just any engine. It was a monster that could generate power levels that made American engines look like lawnmower motors. Here's where it gets crazy. The RD-180 uses something called oxygen-rich stage combustion. Think of your car engine. It burns fuel once and throws away the exhaust. But the RD-180? It burns its fuel, captures the exhaust, and burns it again in the main chamber. It's like getting twice the power from the same amount of gas. The chamber pressure hit 24.5 megapascals. To put that in perspective, that's like trying to contain the pressure of 3,500 pounds per square inch. Enough to crush a car. The metal had to be coated with special ceramics just to survive. But here's the betrayal nobody talks about. America promised they'd only buy a few engines, learn the technology, then build their own. They lied. For the next 2 decades, every single American military launch, every spy satellite, every classified mission, depended entirely on Russian engineering. The cost was astronomical, $9 to $10 million per engine. But money wasn't the real issue. Dependence was. What if Russia decided to cut America off during a crisis? The entire U.S. space program could be held hostage by Moscow. Then this tech billionaire with zero rocket experience showed up. While Boeing and Lockheed Martin were writing $10 million checks to Russia, Elon Musk was building rockets in a Texas field. The establishment laughed. Rockets aren't software, they said. You can't just iterate your way to space. Musk saw what they missed. The problem wasn't just power, it was economics. The RD-180 was designed as a throwaway engine. Use it once, throw it in the ocean. That's fine when you're launching twice a year. But what if you want to launch twice a week? Here's where Musk made the bet that shocked the industry. Instead of kerosene like the RD-180, he chose methane. Everyone thought he was insane. Methane was the fuel nobody wanted to touch. It was complicated, expensive, and unproven. Kerosene was reliable. Every major rocket used it. Why risk everything on rocket fuel that might not even work? But Musk understood something the experts didn't. The future of spaceflight wasn't about single-use rockets. It was about reusability. And reusable engines need to be clean.